So it's my pleasure to present this work that has been done in the ENS Lyon, the Laboratoire de Physique. And unlike most of the talk that we've heard to now, I will be strictly speaking about classical physics. So I've been invited here to make a preview of what we're doing, still doing in the study of the energy information handling in the classical world. And this is mainly the work of the PhD thesis of Salomon Dago. Thank the organizers for inviting me to give this talk, and also thank all the previous presenters because I was expecting to suffer a lot because I don't know a lot about quantum physics, and actually I learned a lot during this conference. So thank you all, and I hope that you can also gain something from my presentation. So I will be talking about the Landauer limit, which was predicted in the 60s, so like 60 years ago. And this limit is about how much it costs to erase 1 bit of information. And the prediction of Landauer is that at temperature T, well, you have to spend an energy which is kT log 2. And at room temperature, this is this tiny amount of 10 to the minus 21 joules. So where do we stand with respect to this limit here? So this is a kind of computation per kilowatt hour you can perform as a function of time here. In the early ages of computing, it was only a few hundred operations per kilowatt hours. And there's a Fenelon-Menching law here that has been observed by Kumi, which is an exponential growth of the efficiency of handling information. And if we project this line here in about 30 to 40 years, we will hit this limit predicted by Landauer. So this is maybe something we can start to worry about. But I won't be talking about this. I will be mainly talking about this point here. Why do we have this limit? And, well, how to explain it. So the beginning here is that we have a system, a bit of information, which take either two values, 0 or 1. And when you erase this information, you get, in the end, only one value. So doing this in your physical system, whatever is the memory made of, the number of states goes from 2 to 1, so you decrease the entropy of the system. And if you decrease the entropy of the system, then you have thermodynamics that tells you that you need to expel some heat in the environment of your memory here. So there's a memory, and there's some heat which is expelled. Obviously, you have to provide work for this heat to exist, so you are making work here on the memory. And then the second law tells you that both of this work and heat here should be greater than, well, the loss of entropy, which is k log 2, so kT log 2 is the limit. So this is a way of understanding things. And my presentation here will be about how to demonstrate this experimentally. How close can we get to the bound? What happens if we have fast operation? Because the equality here would be for quasi-static operations. And can we understand this limit here, not from an entropic point of view, but from an energetic point of view? Okay. So let's start with the requirement of my experimental demonstration. I want something as simple as possible, so I will just take 1 degree of freedom, which will be x here. I want 2 states, 1, 0, and 1, 1. And if it's a memory, then it has to be stable, so each of these states here have to lie at the minimum of a potential of energy. So I have a B-stable potential here with a barrier height here, which is separating the 2 states. Since I'm playing in the kT scale, I want this barrier height here to be of the order of kBT. If I have something here which is several million of kTs, then probably I will have to pay a lot to cross this barrier. So this is one of the requirements of my system. Obviously, if I want to modify the memory, I need to be able to play with the potential. So I need a tunable potential. And for instance, if I want to write a 0 here, what I can do is well, lift the right well here till there's only one well left, and everything will slide down here, and I will have erased my information for a 0. And the last thing I need to do to perform my experiment is I need to measure something. So I need to measure either the heat or the work at the level of this kT scale. Okay? So these are many requirements. Maybe I'll start with the last one. To work on thermodynamics at these scales, what we need as a framework is stochastic thermodynamics. So basically, you can see your degree of freedom here with some Langevin equation, and then you have some noise which is due to the environment. And well, there's a way to define work and heat in this framework. So if you know about this, then well, this is what you know, and if you don't worry. You just have to remind that we can measure those two quantities by following the trajectory of the position as a function of time. Now, I'll be working with undammed system, so there's also a mass term here in this equation, and the only modification to the common framework of stochastic thermodynamics is that now I have also kinetic energy to consider. But in the end, what I have here is an energy balance that says that the total energy variation, kinetic plus potential, is equal to the work I input on the system minus the heat that goes into the environment. Okay. So the first experiment that was able to tick all those boxes here was done in Lyon by Sergio Ciliberto and collaborators. And it was using optical tweezers. So there's a small bead here, which is in water. And when you focus a laser in this environment, well, the bead here is trapped at the waist of your laser. So it's kind of making a minimum of potential here. So now if you make two lasers side by side, you get this kind of situation here where you see that the bead is hopping from one trap to the other. This is because in this case, the barrier height here was low, so just thermal activation was enough to go left to right. So this is a bad memory here. If you want a good memory, what you can do is increase the power of the lasers, and the traps are very stiff. And, well, this is not the corresponding video, but you would be either trapped left or right, and you would have your memory. And now, I'm able here to change the height of the barrier. Now, if I want to also change the shape of my potential, what I can add here is a flow of the fluid, which is embedding the bead here. And for instance, here, by putting a flow on the left, I will have favorize the left well, so I can lift here the right one, and then empty everything to the left side and write my zero. So this experiment was done, and this is a kind of measure that they get. So this is the heat, the mean heat of the experiment, as a function of the time you take to make this erasure here to the left. Okay, and if you wait a long enough time, so tens of seconds, you see that the heat that you are expelling in the environment is slowly converging to this log2 limit in kT units. So this is actually the first demonstration of the Landauer bound for information erasure. Now, so the shape of this dash curve here, which is shown, is log2 plus b divided by tau. Tau is the time that you take to do the experiment. And so in the quasi-static limit, you reach the bound. And at low, well, if you are too fast, then you have to some overhead to this Landauer bound. Okay. The b factor here is some time constant. And it has to be linked with some time constant of the system. And actually, if you take, for instance, the diffusion time from one position to the other here in water, you get something which is here, so the distance squared divided by the coefficient of diffusion d, and it's of the order of a few seconds. So, well, the characteristic time that you get here is something which is linked to the properties of your system, is the characteristic time of the system. Several of our experiments were done in the same kind of overdamped geometry, and, well, they all get with some prefactors here exactly the same scaling. So everything is decaying here as a function of the diffusion constant. So somehow it means that this overhead that I have to pay, the B factor here, is proportional to the viscosity, to the damping in my system. So if I want to have a system with a very low overhead here, I need to find some system with a low viscosity. So a bead in water is clearly not a good memory. You would have guessed probably, but okay. So my experiment here now is, can I do something where I have the same kind of system, but with a low viscosity? And my proposal here is to use a small cantilever. So this is the kind of cantilevers which are used in atomic microscopy, but here there's no microscopy image. It's just a small resonator, okay? So I have 1 degree of freedom, which is the deflection of this cantilever. I can measure it with very high precision. Here I use an interferometer. I can measure this motion here with a precision of 1 picometer. And the thermal noise of this object is about 1 nanometer. So this is the blue curve that you are seeing here. Those are the thermal fluctuation of this object, the Brownian motion. And you can have a very good resolution for this. Now, the mean position here of your cantilever, you can tune this by adding some electrostatic force. So you have applied here voltage between the cantilever and some electrodes. I have a force here which will depend on the voltage. And for instance, if I take a square pattern here for the voltage, I just displace the center of this harmonic trap. Okay, so I have this cantilever which can oscillate in 2 positions. That could be my 0 and my 1 if I decide. Okay, but this is not a bistable potential. What I have here is just a single potential which I'm moving with the voltage that I apply. This is an oscillator. The quality factor here is about 10. And the typical time scale that I have for this system is of the millisecond order. So it's much faster than what we had before. Okay, so the question is now, can I have a bistable potential? How can, from just 1 single potential, build something which is 2 wells? The trick here is to use a retroaction. So I use a feedback loop. I measure the position, and I will adjust the value of the voltage which I apply, so the electrostatic force, as a function of the position. If I do this fast enough, so fast with respect to this millisecond scale, then I can construct whatever landscape I want. And this is what we have done by using here just a sine function. So if my deflection is positive, then I center the well here in around 1.5 in units of sigma. Sigma is the mean square deflection due to the temperature. Okay, and then if the deflection gets negative, so if I cross the 0 here, what I will do is instantly I will switch my well center to this minus 1.5 here, okay? So I have just a single well, but I'm translating very fast as a function of position. And what I'm constructing here is a virtual bistable potential. And this is a measurement that we get in the end, so in blue, and the model that we have in red. So this is just, you take 2 parabolas and you stick them, and this is the kind of potential I can construct with the system. Okay, so now I have a bistable potential. I have the KT scale. You see here the scale of UKT for this barrier. It's tunable. I have 1 degree of freedom. I tick all the boxes, and I can do the same erasure experiment as before. To control the barrier height here, what I can do is just change here the distance between the 2 wells, and this is a parameter lambda here in my potential well. Okay, so what does it look like for an erasure? So I have my 2 wells here. The left and blue, left and right states are just a random oscillation, and then I'm just getting the 2 wells close together, merging them, and then translating everything on the left side before recreating an empty well. I have erased the information, and in this protocol, which is represented here with the position as a function of time, so you have the fluctuation here. First, you are approaching the 2 wells. At some point, the barrier is low enough so that you can cross and jump from 1 well to the other. Then nothing happens, and finally, I translate things back to 0, and everything, whatever the initial condition, is in 0. The time scale here is a few hundred milliseconds, so this is slow with respect to the time scale of my system. So this is quasi-static. And I can expect here to meet the Landauer bound. And indeed, if I measure the heat and the work, I can measure both in this experiment. For a few thousand trajectories, I get the 2 distributions which are here, so dark blue for work and light blue for heat. And you see that the mean value of those distributions here of work and heat are log 2 with something like 1% precision. So the fact that I can do, experiment very fast. It's less than a second to make one experiment. I can make a few thousand in an hour. So I have a very high statistic and a very high precision with respect to previous experiments. So this was a quasi-static experiment here. Now I can try to do the same kind of experiment, but faster. And if I do this, so this is the time I take to merge the two wells. And again, I will depart from log 2 with the same 1/tau law, of observation. This is the same kind of behavior that they were seeing previously. So if we compare the two experiments on a single graph, so this is a time scale here. This was the previous experiment. This is the most recent one. You see the same kind of scaling, the same limit, and you see 3 orders of magnitude here in time. This is just because the intrinsic, relaxation time of both experiments is just 3 orders of magnitude different. Okay, so there's no surprise here. So now let's think again. So I was telling here that what you have to pay is probably due to viscosity in this end here. And in my system, the viscosity is very low. So, there's a question here. What do I have to pay anything if I'm going to 0 viscosity, right? And actually, if you I just take the translation part of the well. When I have a single well, I'm then translating, and I'm measuring the work and heat here. This is a curve which is here, which is going to 0, actually, if I'm going slow. And the overhead here to the log 2 is not enough to explain why we're departing from log 2. So viscosity is not the only thing that makes me pay more than the Landauer bound. And so that's something to understand here. So let's see. Now I will look at what's happening during the experiment. So during my compression, during the merging of the two wells here. And I'm plotting here the power I'm giving to the system as a function of time. Okay? So you can just forget about the formulas here and look at the graph. So the power that I'm paying, this is during the merging of the two wells. You see that initially it's 0. They don't see each other, the wells, so it's just a translation. Nothing happens. And at some point, I'm able to cross the barrier here, and I'm starting to pay something. This is where I have to provide work to the system to do something. And the green shaded area here corresponds to the translation. Translation is free. It doesn't cost anything because I have a very low viscosity. So to understand this, I'm paying only here during the last part of the merging. I will propose a very small toy model, which is a single particle gas. So imagine that you have a box here. It has 2 sides. That's my 0, that's my 1. And then I want to erase information, so I want to put my single particle gas on the left side. So if I do this, I just make a compression of the gas. And yes, now I understand where I have to pay something. I'm compressing a gas. There's a piston, it's thermodynamic, there's always a piston somewhere. So I'm compressing something, and I have to pay. Okay? So let's say I have a gas, single particle. The pressure is kT divided by V. That's my idle gas. The work is P dV, okay? So the work is kT d log V, and the volume is shrunk by a factor 2, so kT log 2. Perfect. And now I understand from an energetic point of view why I have to pay this when I'm erasing information. Now, and now if I have a translation, I have 1 volt pushing, 1 volt pulling, so this is free. I'm just changing the gas, the position of the gas, nothing here. Okay. If I look now back to what's happening in my experiments, so the power that I get is also kT d log something here, which is due to my experiment. I call this a volume, and I just can't forget about the experiment, but kT d log V, I have exactly the same thing as a single particle gas. Now, let's do this fast. I am compressing this information. What's happening if I'm compressing a gas very fast? Well, it doesn't have time to expel heat in the environment, so it's heating. So the T here is actually growing, and I have to pay more than kT log 2 because just T is not the temperature of the bath anymore. Okay? And actually, if you look at the power again, here's a function of time during my experiment. I have some oscillation here during translation. This is just, the particle bouncing back and forth, but the average is 0. And what I'm paying above the quasi-static theory here is just when, in the last part of the compression, when the system is heating. Okay. Do I have a proof that I actually heat the system? Well, I have an unknown system, so I can measure the speed. If I have the speed, I have the kinetic energy, and the kinetic energy is the kinetic temperature of my system. So I plot here the kinetic energy as a function of time for the slow and fast operation. For the slow operation, the kinetic energy stay around 0.5 kT. So this is quasi-static, which is what I expect in equilibrium. Half kT, perfect. And then when I'm going fast, you see that here, just at the end of the compression, I'm heating the system, the temperature is rising. So this is my experimental proof that actually the memory is heating in this part. We can model this. So we can write a bunch of equations here, but let's forget about this. I have work, which is coming into my memory, and then heat is going only slowly into the environment. So this is why it's heating. The equation that tells me how heat is going to the environment is this one. So that's the heat rate. And it's, proportional to the difference of temperature between the system and the environment, as you would expect. And here is the quality factor of my resonator, meaning that the lower the viscosity, the higher is my quality factor, the longer it will take to expel heat from the memory. So what I could do here is to change this quality factor to something even higher and see if I'm heating more. And this is this experiment. I take the same kind of cantilever, but I put it in vacuum, so the viscosity of the environment is even lower. Now I get a quality factor of 80 here, and you see that indeed the kinetic energy here is rising more, and the decay is lower because it takes longer time because, actually I'm kind of insulating my system from the environment. Okay. So I have the theory for this is working. It's perfectly describing the experimental data. And now maybe there's a question here is what if my quality factor here goes to infinity? So I'm taking the adiabatic limit in the sense that if the quality factor is going to infinity, then the heat exchanges are going to 0 in the time scale I'm interested in. So the entropy is conserved. If the entropy is conserved, then, we can show that it means that the product temperature time volume is the same, is conserved during the experiment. So if the final volume is half of the initial volume, then the final temperature has to be twice the initial temperature, meaning that in the adiabatic limit, my temperature here will rise to 2, so the kinetic energy will rise to 1 here. So we did all kind of measurements here, and at long time, low speed, we arranged the Landauer bound, and for systems which are in the high quality factor, you have this adiabatic limit here, which corresponds to the red dots for the measurements, which are indeed close to what we predict with our model. So maybe the takeaway message here is that we have a model that can model what is happening to heat and work during the erasure. And it's indeed KT log V, except that T here can depend on the procedure that I'm applying. Okay. What's more? Well, I've described some operation that we can do on 1 bit, which is erasure, so reset to 0 or reset to 1. And there are only 2 more operations that you can do with a single bit. An operation which is 0 goes to 0 and 1 goes to 1, so that's old. This is an easy one. We didn't do anything, so there's no energetic exchanges here. And the last operation here is the operation not. 0 goes to 1 and 1 goes to 0. This operation we can also perform in our system. I will not go into the experimental details. But this one is a reversible operation. If you have the final state, you know where you come from. So if it's reversible, there should be a way to do this also reversibly in a thermodynamic point of view. And so in this case, there is no KT log 2 to pay. So you expect that the power, that the work that you have to perform on the system here could go to 0. And indeed, in our system, we found, for instance, 0.4 kT, which is lower than log 2. But actually, this is in 1 over the quality factor. So going into higher vacuum or having less viscosity would even lower this number here, and we could go to 0. Now, for the reset operation, I mentioned here that we have a generic way of describing things. And one of the important things here that we notice is that, so I have initial temperature, and if I erase information, I get twice this temperature as the final temperature of my system. Now, if the heat exchanges are bad with the environment, then the system may be still hot when I start a new operation. And then I will double this temperature again and again. And then at some point, the temperature will be comparable to the barrier between my two states, and my bit will lose its fidelity because, well, it will just because the temperature up from the 0 to 1 state, and I have no way to be reliable in this case. So there's a trade-off here of if you want to go fast, you don't want to eat too much, but you don't want too much viscosity. So there's probably some optimum to be found. And we were able, in the end, to plot this kind of heat maps. So what you see here is I can choose the quality factor of my memory. I can choose the erasure speed I'm working with. And then blue is low energy here, and red is a lot of energy in KT, a few hundred. And then if it's going black, it's because you are not reliable anymore. So if you want to have a reliable operation and not too much energy to spend per operation, the optimal curve is something like this white line here. So you have an ideal quality factor of about 20, 30, or something like this. Okay? So that would depend on the mix of operation that you do, how much erasure, how much bit flip. But anyway, if you have a model for your memory in terms of quality factors, then we can predict where you will be standing when you give the speed of operation. Okay, it's time for me to conclude. So all the points that I tried to convey during this presentation. This experiment is a very nice platform to make fast operation and have high statistics in stochastic thermodynamics. We have an illustration of the Landau round, KT log 2, and it comes from compression of going from 2 state to 1. If you're going fast, then you are heating the system. And in the adiabatic limit, well, instead of paying KT log 2, you have to pay just KT. That's what we demonstrated. Okay, and maybe two perspectives for the future. The thing that we're doubling the temperature is because you are putting some work into a system, and there's no way to expel heat. But now, imagine that I have a way to increase the heat capacity of my system. Then I'm giving it work, but it has a very large heat capacity, then the temperature will not raise that much. So that would be a way to mitigate the heating of the memory and having reliable memories that you could use repeatedly without any problems. So this is one way, one direction that we're pursuing. And another idea. So in the end, when I erase my adiabatic memory, I have something which is hot, and then I have a bath which is cold. So maybe I have a way to extract some energy from this and reuse this for some other process. And that would be also a way to lower the energy cost of information processing from a classical point of view. With this, I'll leave you here with some references. You can go to my webpage if you want to download some. And I'm happy to take some questions.
Hello.
Oh, thanks a lot for the presentation. It works. At the very beginning, you showed this graph with some of the exponential growth in number of computational steps per what I think with the Landau limit. Yeah. Do you have like some figure in terms of how much the erasure steps or the irreversible steps in a computation somehow affect the overall energy or consumption of a classical computer?
So I don't have any number, but this is just a guess here. But the distance between this point here, well, today and the limit is like several orders of magnitude. So I suspect that this is not the main issue for now. I was just here giving an overview of where we stand when we speak about this non-hour limit. This is something which is not a problem today.
Yeah.
Okay. Yeah. But could be anyway interesting to have some ideas of how to deal with this in the future if we get to this point.
Thank you.
Any other question?
Very sorry for the Well, thank you. I have a tricky quantum energy initiative question. Like, do you know how does this Landauer principle translate for erasure of qubits, and if it can be measured in any systems?
How would this translate into the
How does it translate to a qubit, and which systems could we envision to check?
Well, I think that was like my first word to say that I'm not from the quantum world, so I'm sorry, this is a question for you guys. But maybe more seriously, from my understanding, everything that's true in the classical world would just translate as well. A main difference may be that in most of the quantum computers that I've heard during this week, they are working at temperature which are millikelvin, so and KT log 2 is very, very low in this region.
Yes. Should I speak up or? Oh. I have a difficult question. In the heat, obviously, you infer it by looking at the trajectory of the particle. And I guess in the future, I would really like it if we could externalize that work or measure the heat.
It was hard to hear.
Okay, I say again. So,
Better.
excellent.
So what I'm saying is the heat and the work that you're currently inferring comes from the trajectory that you measure the whole time, which is standard and it's very nice and it's correct. But of course, conceptually, you would very much like the work to go into a separate degree of freedom, and you would also like the heat to be abiding in the heat bath. And I wonder whether you have any ideas of how your platform could potentially realize that measurements of either of those.
So about the work, maybe I have just two here. Okay. So when you are performing some work here, what you do is that you have this electronics force here, which is working on the cantilever. And what you have here is like a capacitor between the cantilever and the electrode. Okay. So if you have some electrostatic work, it's actually meaning that there's a current which is flowing here outside. So you could put some electronics outside the machine and detect this current, and then if you have some current, then you can use it somewhere else. Okay? That's one answer for the work. Now for the heat, we have a way to measure the heat which is going into the environment. No, I don't. But I have some clues that the heat is actually here. For instance, because I can measure the kinetic energy of my system and that it's warming up. So this is, to my knowledge, a very nice proof. Nice proof that we have actually heat which is here. And if we have the heat capacity of the system and the temperature rise, and this is another way to measure the heat than following the trajectories.
I think we have one last.
Yes, sorry, maybe one less tricky question. More experimental, like which precision do you need on the measurement of the position to be able to infer the work and heat? Like, do you have relative requirements?
So the precision that you have here is not limited by the measurement of the interferometer, because the signal to noise, well, that's a noise to noise ratio, but the thermal noise to measurement ratio is 1,000. So that's not an issue here. The problem is more that this cantilever is not only an oscillator, it has several modes of oscillation, right? And the high frequency mode of this object, we are able to kill the mode 2 just by putting the laser in the right spot, but then we have mode 3 of oscillation of this cantilever. And this one is like contributing to a few percent more noise on the system. This is higher frequency, so we try to filter this out. But then, if you filter, you are dephasing your signal. So then you have other tricks to do with building this double well potential. Well, we kind of trying to make the best out of this. Why we are limited, for instance, to quality factor of about 100? Is because if we go to higher quality factor, which we could do in our experiment, then this construction of the virtual potential here is not working so well. So this is one of the limitations of the system. So I would say that for now we have about signal to noise ratio of 50 to 100 or something like this, which is good, and enough for this kind of experiment. Anything which would be lower would just increase the error bars that we have on the work and heat. And for now, we can reach a few percent. So maybe a factor 10 more would be okay. But well, we're pretty proud of what we're doing for now.
Well, thank you. If there are no other questions, oh yes.
I have a kind of engineering question. What's very interesting is when you look at the roadmap, it goes up to 2040, I think, in the way we could reach the Landauer limit. I was trying to match that with the IEEE roadmap on transistors and memories. And it's interesting because when you look...
You mean this map?
Yeah, there was another one before, but whatever.
Okay.
And interestingly, the way the semiconductor industry planned their roadmap is not getting very close to this limit, at least in the same time frame. So I was thinking about, have you got an idea of what kind of technology would enabling this industry to get much closer to this limit? Which kind of transistor or two-level systems? It's a TLS, electronic TLS that could be fitting that.
So here we'll be talking about things I don't know anything about. So you have to take my answer with caution. But from my point of view, you are in a system where mostly you have some resistive dissipation and some capacitance, which are due to the memory and everything. So you are mostly in an overdamped system. And we say that if you want to go to better, energy efficient system, you have to go rather on the side of having something which is resonant. Okay, so it would mean include some inductance in your circuit, so as to have some oscillators, and so to work as a frequency where the capacitor and the inductance compensate each other, so that you are close to the resonance. But,
so it's interesting. It means a very different design compared to what we have in CMOS right now. Mm-hmm. Okay, it gives insights on what kind of roadmap could be created in the classical world. Okay, thanks.
Okay.